Welcome to Lesson 1, Introduction to Drinking Water Systems. This 1-hour lesson will help you understand what water is, where water is, how water is used, and the makeup of a small public drinking water system. Section 1.1, What is water? This section describes water and its important properties. As an operator of a small drinking water system, you must understand water and its important properties very well. Section 1.2, Where is water? This section summarizes water sources and the distribution of water nationally and statewide. Section 1.3, How is water used? In this section, you will come to understand the typical uses of water and demands for water. Section 1.4, What is a drinking water system? Typical small drinking water systems are described with specifics on why these systems are needed and how they are classified for regulatory purposes. Section 1.1, What is water? Our bodies contain 70% water. Water carries nutrition throughout our bodies and rids us of waste. Without drinking water for 4 to 7 days, our blood becomes thick and contains a high concentration of toxic waste materials. We become delirious and unable to function. Death is not far behind. Water is often called the universal solvent. Given enough time, it will dissolve almost everything that it comes in contact with. As water flows through gravels, fissures, and sands in the Earth's crust and flows over the top of the ground, it picks up minerals, microorganisms, dirt, and bits of plants. Some of these materials are carried along by the water due to its speed. Others, such as minerals, are dissolved in the water. Water, like many other fluids, also has the ability to dissolve gases, such as oxygen, or O2, and carbon dioxide, or CO2. Dissolved oxygen in water allows fish and other aquatic life to live. Without oxygen, fish like humans would die. The gills of the fish allow it to filter dissolved oxygen directly from the water. The water molecule is composed of 1 atom of oxygen and 2 atoms of hydrogen. This molecule is given the chemical symbol H2O, H2 for 2 hydrogen atoms and O for 1 oxygen atom. Notice that the 2 hydrogen atoms are at one end of the molecule. The hydrogen atoms are positively charged. When the hydrogen atoms attach to the oxygen molecule, the whole molecule effectively becomes polarized with negative and positive poles, much like a battery or a magnet. Because it has both negative and positive charges, it is much easier for it to attract other material. This is one of the reasons it is the universal solvent. Water has another unique property. It is the only material that is found on Earth in the 3 basic states at standard temperatures. These states are solid or ice, liquid or water, and gas or water vapor. Explore the temperature-related properties of water by adjusting the slider to each temperature set point. Water molecules in motion. The water molecule, like other molecules, is in constant motion. The rate of this motion is directly related to the temperature of the water. As the temperature is reduced, the rate of movement of the water molecules slows and the molecules get closer and closer together. The water molecule moves slowest when the water is in the form of ice, and fastest when the water is a vapor. At 4 degrees Celsius, or 39 degrees Fahrenheit, water molecules are as close together as they're ever going to be. The volume that a set amount of water occupies is at a minimum at this point. Below 4 degrees Celsius, or 39 degrees Fahrenheit, the molecules are moving so slow that their electrical charges begin to cause the molecules to line up in a pattern and form crystals. At 0 degrees Celsius, or 32 degrees Fahrenheit, and below, water crystals are fully formed. This crystal formation allows the molecules to line up in a way so that they occupy a greater space than they did before freezing. Water is one of the few compounds that expands when it freezes. This expansion is what causes water to break a bottle or pipe when it is frozen. Section 1.2, Where is water? Water sources. The sources of water on the earth are divided into two categories, surface water and groundwater. Surface water is water that is found in the oceans, lakes, streams, springs, and ponds. This is the source of drinking water for some of our largest communities. Surface water is exposed to the atmosphere and is affected by ambient conditions. Groundwater is the water below the Earth's surface. Hydrologic cycle, how it works. The amount of water in the atmosphere, lithosphere, and hydrosphere remains constant. Water is continually recycled by the action of plants and the sun. Let's pick up a droplet of precipitation and follow it through the cycle. Precipitation in the form of rain, snow, or sleet falls toward the earth. As the precipitation falls toward the earth, it can pick up contamination in the form of minerals and toxic materials from industrial air pollution and natural pollution such as dust from a volcanic eruption. On its fall toward the earth, some of the precipitation evaporates. The amount of evaporation is dependent upon several factors such as humidity, air temperature, and wind. There is a significant amount of precipitation that is recycled back to the atmosphere before it ever strikes the ground. Precipitation hits trees, brush, and grass. Some water evaporates directly from the leaves, while other water flows down the outside of plants to the ground, or strikes the ground directly, then runs downhill. This water flow picks up contamination from organic or inorganic matter. The water flow accumulates in lakes, streams, ponds, and rivers. Most rivers will eventually run into the ocean. These sources are referred to as surface water. A large quantity of the water that forms surface water will be evaporated back into the atmosphere. In fact, in most of the world, this is the largest single loss of surface water. Some of the water that is running along the Earth's surface seeps into the soil. This process is called infiltration. As the water infiltrates the soil and moves downward, some is taken up by the roots of trees and other plants. The water that is taken in by plants moves upward and is given off into the atmosphere through the leaves of the plants in a process called transpiration. This transpired moisture mixes with the moisture that is evaporated from surface waters. This combined process is referred to as evapotranspiration. The water not taken up by plants continues to move downward in a process called percolation. This water continues to move downward until it collects in gravels and sands called aquifers. The water continues to slowly move toward and into adjacent lakes, streams, and the ocean, where it is evaporated back into the atmosphere. Springs are formed when the edge of an aquifer is exposed to the surface. Water can exit the hillside or mountain, run along the ground surface, and eventually mix with surface water. Groundwater and surface water eventually mix and are evaporated back into the atmosphere and form water vapor. This vapor is condensed by atmospheric conditions and forms precipitation, which falls to the ground, and the cycle begins again, providing us with clean, fresh water for our water systems. The total of all water in the world is approximately 306 million cubic miles. Of this total supply, 296 million cubic miles are in the world's oceans, and about 10 million cubic miles, or 3% of all the water in the world, is available as fresh water. About 75% of the fresh water is tied up in the polar ice caps, soil moisture, and atmosphere, while 25% of the fresh water is in the groundwater supply, leaving 0.3% of the fresh water in the lakes and streams. The total usable groundwater supply is estimated at 1.1 million cubic miles. The lakes and rivers represent 0.03 million cubic miles of fresh water. This gives a total of 1.1 million cubic miles of usable fresh water. Of the usable fresh water, 97%, or 1.1 million cubic miles, is in the groundwater supply, and 3% is in the surface water supply. Within the continental United States, 77.3% of the public water systems use groundwater, and 18% of the systems use surface water. 4.7% of the systems in the U.S. use a combination of surface water and groundwater. On the other hand, 68% of the population is served by surface water suppliers, while only 32% of the population relies on groundwater supplies. In the continental United States, 37 of the 100 largest communities use surface water. This is because the majority of these communities are built next to surface water sources, including 10 that are built next to the Great Lakes. In the West, communities such as Los Angeles, San Francisco, Portland, and Seattle all utilize surface water. In Washington, 84% of the population is served by public water systems. Of the approximately 200 federally defined public water systems, only 5% of those systems use surface water, while 95% use groundwater. Some of the large cities in Washington use a combination of surface water and groundwater. Groundwater systems are used throughout Washington. Many larger cities in Washington use only groundwater, such as Spokane, Pullman, Lacey, Ellensburg, and Kent, to name a few. Much of central and eastern Washington is without a surface water source. Thus, many of the federally defined public water systems in central and eastern Washington rely solely on groundwater. Section 1.3, How is water used? Categories of water use. The consumption of water is often divided into categories depending on its intended use. Typical categories are industrial use, agricultural use, domestic use, and public water supply use. Did you know? Industry in the United States uses an average of 150 billion gallons of water each day in order to produce the products that we all use. The average use of water in the U.S. is 184 gallons per day per capita, which is used for many different purposes throughout the day. In some areas of the country, the usage may be as high as 400 gallons per day per capita. Industrial use. Steel. 270 tons of water is used to make 1 ton of steel. Paper. 250 tons of water is used to make 1 ton of paper. Gasoline. 10 gallons of water is used to produce each gallon of gasoline. And seafood. The processing of seafood requires large volumes of high-quality water. Agricultural use. Even the food we eat requires water to grow and process. Each loaf of bread requires 115 gallons of water to produce, and each gallon of milk requires 16 gallons of water for processing. Domestic use. For laundry, 20 to 40 gallons per load. For showers, 20 to 30 gallons each. For baths, 30 to 40 gallons each. For flushing toilets, 1.6 to 7 gallons per flush. And for drinking, 1 to 2 quarts of water per day. Public water systems. Public water systems in the U.S. deliver for domestic, public, industrial, and agricultural use. Usage ranges from a few gallons per day to many million gallons per day. Water usage and consumption is best monitored through the use of meters. The average daily demand for your utility should be determined for each month and recorded as part of the routine records for the water system. Minimizing the average daily demand can reduce the cost of upgrading the system. The water system's pumps, storage, and treatment must be designed so that the system can meet peak hour demands and fire flows without stressing the system. The peak hourly demand is best determined from a chart recorder. Normally, a peak day ranges from 1.5 to 3 times the average day. Section 1.4. What is a drinking water system? Composition of a water system. 3 primary components of a water system are the collection, treatment, and distribution subsystems. Operators manage and maintain these system components in a safe manner that meets the needs of the customers. Collection. The collection system in a public drinking water system can include dams, intake structures, screens, pumps, and piping. For instance, groundwater is collected by using a pump and a well. Treatment. The treatment process varies from community to community, but typically includes turbidity and microorganism removal, possibly color removal, and nuisance chemical removal. Distribution. Most distribution systems will include pipes, valves, fire hydrants, storage tanks, pumps, and house service connections. Did you know, on a worldwide scale, 1 person dies every 9 seconds from a waterborne disease? At the turn of the century, there were 360 typhoid deaths out of every 1 million people. With the installation of water treatment plants and disinfection, the number of deaths was reduced to 1. This reduction was enhanced by improvements in personal hygiene. Diseases that are carried by the water are called waterborne. The organisms that cause these diseases do not normally live in the water, but are transported by the water. Examples of typical waterborne diseases are cholera, typhoid, dysentery, polio, hepatitis, and giardiasis. All of these diseases can be prevented from spreading through a water system with proper treatment and disinfection. When the water produced by a system is objectionable because of odor, taste, or appearance, the customer will often seek another source for their drinking water. While looking, tasting, and smelling good, another source could contain microorganisms and/or chemicals that are harmful. This last point is critical, but often overlooked in the operation and management of a public water system. The primary purpose of a public water system is to protect public health. The water system serves as a line of defense between disease and the public. Properly operated systems protect public health by the following: the removal and/or inactivation of pathogenic organisms, including bacteria, viruses, and protozoa, the reduction and/or removal of chemicals that can be detrimental to health, such as arsenic, nitrates, lead, and copper, and by providing quality water, thus discouraging the customer from seeking other sources, which may end up being a contaminated source. Classification of systems. Water systems are classified using various methods and criteria. The most common criteria for classification are type of source and population. In addition to this classification, water systems are classified based on the state and EPA specifications. Classification by source. Common source classifications are surface water, groundwater, and groundwater under the direct influence of surface water. Classification by population. The U.S. EPA has classified systems according to population. This classification was developed in order to allow the EPA to phase in regulations so that systems serving the largest segments of the population were addressed first. EPA classification. In order to apply drinking water regulations uniformly across the United States, the EPA classified systems into three categories: community water systems, non-community water systems, and non-transient, non-community water systems. State-specific classification. Many states have their own classification system, including Washington. Public water systems in Washington are classified into Group A water systems and Group B water systems. Washington classification of systems. In Washington, all systems except those serving only one single-family residence or less than 5 residences on the same farm are public water systems. Group A water systems are water systems that regularly serve 15 or more residential connections or serve 25 or more people per day for 60 or more days per year. Group B water systems are water systems that serve less than 15 residential connections and less than 25 people per day, or serve 25 or more people per day during fewer than 60 days per year. Community systems regularly serve 15 or more year-round residential connections or 25 or more year-round residents for 180 or more days per year. A non-community system is any system that is not a community system by definition. Transient non-community systems serve 25 or more different people per day during 60 or more days per year, or serve 25 or more of the same people per day for less than 180 days per year and during more than 59 days per year, or serve 1,000 or more people for 2 or more consecutive days. Non-transient non-community systems serve 25 or more of the same people per day for 180 or more days per year. To complete this lesson, you must first take a quick quiz. Click on the button below to continue.